Okay, now in the previous video, we looked at how we can achieve these matrix equations for a 3x3 or two spring linked together, and with the establishment of this stiffness matrix equations, we in principle should be able to solve for the deformation of the nodes 1, 2, and 3. Recall that two spring we have 3 nodes under the external loading F1, F2, and F3. So if you write this in the compact form, which we showed it before, let's clean it up. Compact form, we have the force vector F equals the displacement vector U times this stiffness matrix K, right? Now, if you recall your first year linear algebra, now the way we can solve these matrix equations is like, think about it as AX equal to Y. If it's scalar, you can do Y equal to, X equal to Y times the inverse of A. Now there's only one condition you need to satisfy, that is A cannot be 0, because you can't divide anything to be 0, right? Here, if you want to solve U, if we want to solve for U as U equal to F times the inverse of K, right, the matrix inverse, then, right, K should not be singular, or should have a determinant that over K doesn't equal to 0, right? Why we want to do this? Because if we can solve for the deformation, U, what do we know? We can know we will be able to know an important nodal quantity or the physical property at the node, which is the strain, which is this epsilon equal to U, right? Delta U means how much it has been moved, divided by the original length of the element. So this is what happened in 1D case. All right, we want to know the strain or the yield. Now, that's why we need to be able to solve for this U. However, in the case shown above, which is what we have right up here for this big matrix, K is diagonally symmetric. What does that mean? That means the determinant is 0, and generally means the equations has no unique solution, right? What does that mean? So let's go back to the case of 2x2 cases for spring. Now you know that the matrix equations for 2x2 case we have done before is plus k, minus k, minus k, plus k times u1, u2 equal to f1, f2, right? So the determinant of this matrix is basically this one times this one minus this one times this one. So which is k times k minus k times minus k. And if you do the algebra, you can see that this is indeed 0, right? So this matrix has a 0 determinant. And what does it mean by it has no general solutions? Now let's just try to solve these equations by elimination, right? I will try to do this quickly. You can try to work out this algebra after the class yourself. But basically, if you look at the equation 1, and you can express u1 as a function of u2, that would give you f1 plus k u2 divided by k, right? That gives you equation 3. So if you sub 3 into 2, what you're going to get out is something like this: minus f1 plus k u2 plus k u2 equal to f2. Now straight away you can see that this k u2 will cancel out each other. That means no matter what the value of u2 is, the equations will still hold itself, provided minus f1 equal to f2. And that's what we want, because the whole thing is balanced. So the two forces must equal in value but opposite in directions. Now because u2 can take any value, u1 can also take any value you want. Now in this case, the problem is undetermined. So hence the problem is undetermined. Right? But, right, if we give the system a boundary conditions, a boundary conditions, then we will be able to come up with a unique solution for the system, or in this case, the deformation. So for example, if we go back to this equation here, right? So let us just write that back down here quickly. K1 minus K1 0 minus K1 plus K2 minus K1 minus K2 0 minus K2 K2 U1 U2 U3 F1 F2 and F3. Now, as you can see in the slide 37, we have given this some boundary conditions to solve, right? For example, the first condition is that node 1 is fixed to a wall, for example. Now what does that mean? That means U1 is not going to deform anyhow, so U1 equal to 0. That means one of the boundary conditions say this thing is 0 here, right? And we only need to solve for U2 and U3 in this case, so that means only solve for U1 and U2 and U3. So that's the boundaries conditions. And now we can also actually give some values to the loading. For example, we said node 2 and node 3 has a force of 75 Newton applied to node 2 and 3. So if you look at this 1, 2, and 3, we'll apply a force F2, F3, and F2 here, right? What we try to solve in this case is if these two are under loading, what will this force be? So that's an unknown variable. And we know this one is fixed in position, so this U1 is 0, but we'll try to solve what's U2 and U3. So this are also our unknown variable. And we can actually give some force constants. In this case, we say K1 is 50 Newton per meter. K2 is, for example, 75 Newton per meter. Now in that case, we can plug in these value into these equations, and the matrix will have values in there which now look like 50 minus 50, 0, minus 1, minus 50, 125, 75, 0, 75, minus, and 75, right? So now we have 3 equations for 3 unknown. So in principle, that's solvable, right? Now, if you do this by hand, one way to do it is to realize, okay, I have 3 equations, 1, 2, and 3, right? Probably right? A, B, and C, A, B, and C. Now from equation A, if you write that all out, is basically 50 times 0 minus 50 times U2 minus 0 times U3 equal to what? F1. So that basically say minus 50 U2 equal to F1. Okay, so that gives me the first equations. And this is what we call the constraint equations. Right? Why? Because that means no matter what U2 and U3 are, it must satisfy this constraint. Right? This basically determines how the other deformation value will be, right? Now, it basically tells you that if the whole thing is under equilibrium, the force on node 1 must satisfy this relationship with respect to the displacement on U2, right? Because U1 is fixed, okay? Now, if you further look at this bottom two equations, that basically show 125 minus 75 minus 75 and 75 times U2, U3 equal to 75 and 75, right? This one you can actually solve from linear algebra. That gives you U2 equal to 3, say meter, and U3 will equal to 4 with a unit of meter. Now, once you solve this, you can plug this back to this equation and find out F1 in this case is minus 50 times 3, which is minus 150 Newton. So that shows you, once I know the displacement or the deformation on node 2, I'll be able to work out the force that node 1 is being experiencing. So what's the force actually pushing this node 1 in position? So now we show that with a boundary conditions given, right, we'll be able to start solving the stiffness equations for a finite element analysis. And this is what typically happens in a real application, right? So we first set up the whole system by breaking down into individual elements. So we have these general equations that describe the behavior of the system under external loading, which is generally do not have a unique solution because it's a singular stiffness matrix being presented here. By giving us some initial boundaries conditions, for example, the specific loading on particular nodes, or whether some nodes in the structure are fixed, we'll be able to start solving these equations to get a set of unique solutions that will tell me, okay, for example, what's the displacement or the deformation on specific node. So they are the primary nodal quantities that we are interested in. And from there, we can further derive the loading on those nodes, for example, they are fixing positions, right? And in this case, the whole structure, for example, will keep in a stationary state. Okay, so we have so far seen some very simple example based on one-dimensional springs. In the next video onwards, we'll start looking at some more realistic structures and how this equation will start to evolve itself by taking into account the different geometry of the system and different directions of the force loading, etc., etc. Yeah, so we'll continue in the next video.